This section is certainly a lot quicker and with fewer theorems than the last section. I know you'll also like to hear that inscribed angles aren't too tough either. We have dealt with a lot of inscribed polygons, mostly inside of circles before. All of these are polygons that have been inscribed inside of a circle. For every one of these polygons, the vertices lie on the edge of the circle. The same is true of inscribed angles. Inscribed angles have their vertex on the edge of the circle too. Officially, an inscribed angle is an angle in a circle whose vertex is on the edge of a circle and whose sides are chords of that circle. Basically, all that's saying is it looks like this. Apparently, he's friendly too. An inscribed angle opens up and captures a bit of arc. Maybe our inscribed angle isn't too friendly after all, and he is hungry to go eat some arc. That piece of arc that he is going to eat, this one here, is known as the intercepted arc for the inscribed angle. Or if you prefer a less predatory picture, here's an inscribed angle with its intercepted arc. Now that we've been introduced to what an inscribed angle is, what do we know about it? We know that the measure of an inscribed angle is half the measure of its intercepted arc. Before we had central angles, and they were equal to its arc. Here we have inscribed angles, and they are half of the arc. So, for example, if the measure of our inscribed angle here was 44 degrees, then the measure of the intercepted arc would be 88 degrees. That's it. Pretty simple, right? Now we arrive at the first of two very obvious corollaries. They both follow very simply from the fact that inscribed angles are half. You don't even really need to write them down, since you should be able to figure them out anytime you see them in a problem. But here's the first one. Two inscribed angles that intercept the same arc are congruent. So I have had this 44-degree inscribed angle here. That was half of the 88-degree arc. This corollary says that if I had another inscribed angle, which intercepted the same 88-degree arc, then it would be half of 88 degrees, or 44 degrees also. That seems pretty obvious. Sometimes we won't have any degree measures, though. In these cases, I couldn't tell you what any of the measures are, but since the red and green inscribed angles both intercept the same arc, I know that they are congruent. They are both half of the same thing, whatever that measure is. Still, that seems pretty obvious to me. The next obvious corollary says that if you have an angle inscribing a semicircle, then it is a right angle. Well, we know semicircles are 180 degrees, and if an angle inscribes that, then it will be half of 180 degrees. So of course it would be a right angle. It doesn't matter how you draw it, the inscribed angles must be 90 degrees if they are inscribing a 180 degree semicircle. I think that's pretty obvious too. Now we get to a third corollary. This one also follows from the inscribed angle theorem, but it isn't as obvious as the others. It deals with quadrilaterals that are inscribed in a circle like the red one here. Something happens with the opposite angles of that quadrilateral. There are 4 inscribed angles here. Let's focus on this one. This inscribed angle has an intercepted arc, and it is this one here. Now let's consider the opposite inscribed angle. This one also has an intercepted arc. It's this one here. It's interesting to note that for a pair of opposite angles, the 2 intercepted arcs are exactly the full circle. It works with the other pair of angles too if you want to pause and check for yourself. The opposite inscribed angles together intercept a full circle. We know that a full circle is 360 degrees. Inscribed angles are half of the intercepted arcs. So, if a pair of inscribed angles together intercept 360, and they are going to be half, then together they must add up to 180 degrees. That brings us to the last corollary. The opposite angles of a quadrilateral inscribed in a circle are supplementary. I showed you why, but all you need to remember is that they are supplementary. I don't know what the measurements actually are for this picture, but I know for sure that they are supplementary. Most of the time, though, you will have one of the angle measures as you work through problems. Now we get to the last theorem. We want to look at what happens when I have an angle formed by a tangent and a chord. That's this situation here. I have the black tangent line and a red chord. These two things form 2 angles, the green one and the purple one. You should note here that they are a linear pair and add up to 180 degrees. The same kind of thing happens here that happened with the inscribed quadrilateral. The green angle has an intercepted arc. That's this one here. The purple angle also has an intercepted arc. That's this one here. Once again, we have 2 angles whose intercepted arcs together form a full circle. This time the logic is a bit different though. Here we know we have a linear pair that is supplementary and adds up to 180 degrees. The 2 angles intercept 360 degrees. So they add up to 180 degrees, but intercept 360 degrees. That seems like they should be half, right? And they are. The measure of an angle formed by a tangent and a chord is half the measure of the intercepted arc. So these guys, just like the inscribed angles, are always half of their intercepted arcs. That's it for this lesson.